just do that. So my first slide, it's just called, like I said, it's a new concept for many of you. You may briefly discuss it in the first semester, but this time you will spend a lot more time with this, and hopefully by the end of the semester you will eventually get a good grip of what the linear dependence and what linear independence is. So normally when you introduce this concept, you start with the vector space quadruple. So here's my V plus scaling and in general any number field. It might be real numbers, complex numbers, rationals. So here's my vector space quadruple. I fix a set of vectors which I will call, sometimes I will call them x1, x2, x3, sometimes I will call them v1, v2, v3, it doesn't matter which letter you use for that. So if I have a finite set of vectors, n of them, from my vector space, this symbol is a subset, then this set is called linearly dependent if and only if. Look what happens. It's called linearly dependent if you can produce scalars, which I will call lambda 1, lambda 2, lambda n from my field of scalars. So this finite set of vectors, S, it's called linearly dependent if I can produce a set of scalars, n of them, such that if I combine my vectors with these scalars, if I build this linear combination thing, something we already met when we discussed span with you, if I build this linear combination of my vectors with these coefficients, then the result of that will be zero vector. It's one condition which must be satisfied in order to be able to call my set linearly dependent. And the second condition, and such that not every scalar in this sequence, lambda 1, lambda 2, lambda n, not every scalar is zero. If you can come up with such set of scalars, lambda 1, lambda 2, lambda n, so that on one hand, when you take a linear combination, you come up with zero, and on the other hand, not every scalar in this sequence is zero. Obviously, if you have all zero sequences, this will be zero. It's a trivial observation. But if you can come up with a non-trivial combination, not such that not every coefficient is zero, then that will be the criteria to call a set linearly dependent. There is an opposite definition. We call a set linearly independent if and only if it will be just a logical negation of this definition. And logical negation of this definition says this: a set is linearly dependent if and only if the linear combination of my vectors is a zero vector only for the trivial choice of the scalars. If you can prove one way or another, if you can present an argument, and that's this if and only this double arrow, in fact, it's only one way when it makes when it represents any difficulty, because obviously the arrow this way, it is a trivial error, right? If every individual coefficient is zero, obviously the linear combination will be zero. So the arrow this way, leftwards, it's a trivial arrow. But the arrow the other way, this arrow, that's the significant arrow. That's the arrow where you have to invest some time and effort to establishing that arrow. And in every individual example, where you have to prove that the system is linearly independent, your proof will be behind this arrow. You will be putting some argument behind to support this arrow to the right. So if you can prove that as soon as you have the linear combination, that would immediately imply that every individual coefficient is zero, then that will be logical negative of this definition, and in that case, you will call the system linearly independent. There will be plenty of examples in the yellow book for you to practice these tests. Today I will just have one example from the yellow book, and I will show you these two concepts on that example and some other concepts which I can pull from that example. But on this particular slide, I have rather like a canonical example of the linearly independent set. It's a set of free standard basis vectors in the R3. I hope you remember that for these vectors we have this fixed canonical notation: boldface E1, boldface E2, boldface E3. And they are these free, if you think of them within the scope of three-dimensional space, they are linearly independent, because if you build a linear combination of these three vectors, if I build the linear combination of these three vectors, that's the components of E1, these are the components of E2, these are the components of E3. If you equate this combination to 0, in this example, I can easily present the substance behind this arrow. And here's the substance. The left-hand side here, if you just combine all of them together in a single vector, it will be just a vector with the components lambda 1, lambda 2, lambda 3. And if you equate this vector to your 0 vector on the right-hand side in a per component way, that's enough to conclude that individually, your coefficients must be 0. That's why this particular system is linearly independent. It's a relatively simple argument. For the other systems, you will need more advanced, more lengthier argument, yes. But for the standard basis, this is as simple as this. But still, I just emphasize this for you. Every time you prove something is linearly independent, you have to present an argument for this right-hand side implication.